reflection says if you have a mirror here, let's say this is a mirror. Smooth mirror. And you shine a light at that mirror. This light going in is called the incident wave. When that light hits the mirror, let me draw a line that's perpendicular to the mirror. That's this line. That's perpendicular to the mirror. Notice this angle going in, we'll call that theta I, the incident angle. The light, once it hits the mirror, is going to reflect off the mirror as a reflection ray. So this is the reflected ray. And the law of reflection says this angle has to equal to that angle. So the angle theta I equals theta R. That's really what the law of reflection. If you shine a light at a smooth surface, that light will reflect, and that angle going in should equal the angle leaving. So if you're looking at a pond there, and it's a beautiful sunny day, smooth, I said pond, not the ocean. The ocean has waves in it. And you got these rays coming in. This ray will have a reflection that way. If you have another one, this ray will have a reflection that way. This ray, if you have another one, will have a reflection that way. So the angle coming in, the incident angle, should equal the reflected angle, always. Which means if you're standing in front of the mirror there, if you're 6 feet tall, this is you, 6 feet tall, and you want to see your feet, how big the mirror must be? The mirror will have to be 3 feet tall. That's the minimum. Because you want this one to hit it, like on the bottom, and reflect directly to your eyes, or your head there, right top there. So like this is the mirror here, the yucky side of the mirror here. But the incident angle will always equal the reflected angle. Now the one, for example, if you try and watch your head, the light coming off your head, because remember, the only reason we see ourselves, the sun hits us, the rays actually reflect off our body. It goes into that, let's say on an angle here, a little bit of an angle, or my hand here. It might go like this, if this is my hand, and reflects, smudge now. It reflects there, I can see to my eye there. My head should be as high as the mirror actually, but that's not really as high as the mirror there. So I get to see the whole thing. But that's why you need a mirror the half your size to be able to see your full body there. The farthest point possible is your toes, down there. So to see them, that means you need a mirror to be half of your height, because that angle is going to equal the reflection. Now, if the mirror is not a flat mirror, that's a different story. We'll get to that shortly. What will happen if your mirror is not a flat one? You actually have a spherical mirror. Or if this surface is not a smooth surface, let's talk about that too. You go to the ocean and you're on the water there, this is the waves here, and you're standing here playing in the water. You come out, you have the nicest tan. Better than the one who sat flat on their back, just getting their front tan there. The reason when you're laying on your back, only your front is getting tanned. When you flip on your stomach, only your back is getting tanned. When you're on the ocean there, and the rays actually come in, it's a sunny, beautiful day, some of these waves actually will miss you. Like, for example, this wave comes in, it's going to have a reflection that way. That missed you. But this wave here comes in. Let's say we have a wave coming like this on this section. Is going to reflect that way. And well, that's probably going to miss you because you're too short here. But if you were tall, they'll get you there. What about this wave in front of you? Coming down in front of you, it hits the water right there. Notice there's a peak value. It's going to deflect probably down this way because the wave there. So you're actually getting tan from all directions, not just the front, the back there. The waves in the front, when the, especially if this is a high wave like this, if I make the wave really high, any wave that hits this, it's going to deflect that direction. If this wave is high on this end too here, any rays that hits this one, the sun is now past you, it's going to deflect which way? It's going to deflect that way. So you're getting waves coming from all directions at you. Not just the front, the back, the side, everywhere. The US, when they designed the stealth bomber, they designed the stealth bomber on that principle. Normal plane, if you look at them, if you fly on commercial plane, you look at the bottom of the plane, it's so smooth. So the plane looks like this. And if you're flying over enemy area, let's say the enemy starts right here, they usually have radars right there. What the radar does is shoots a signal. As the plane flies over, they're shooting a beam to see if there's any reflection. And there's a receiver right there. It's planted right there to see that. So if actually the beam, if the plane happens to be there, when you cross that path, the reflection will be right there and the receiver will pick you up. And now they know there's a plane up there. What the US did with their stealth bomber, if you look at them, it looks like this. The bottom of the plane. They're all gadgets, not smooth. For that reason. So when the enemy shoots a beam this direction, now the reflection is going to be different here. And if it hits the plane right there on this one, it deflects which way? Up there. They're not getting that signal back. So there's an advantage in this case. There's an advantage not having a smooth surface. It depends what you're trying to accomplish there. But the angle always, theta I equals theta R. Now what happens if your mirror is not really a straight mirror? What happens if you take, for example, an ornament, Christmas ornament, you know it's really shiny, and you drop it and it breaks now. You get a piece of that. Well, it depends which side you're looking at. Is the shiny stuff you're looking on the inside of it or the outside of it? because that will change the outcome.